students, good afternoon. Mr. Fugit here. In our video today, we're going to be looking at one of the problems from your review on test number 5. Specifically, what we'll be looking at today are some of the concepts of work, energy, and power. As always, the problems that we work through are available on Canvas. You can access the problems themselves as well as a key. And here we'll be working through problem number 5 specifically. So I'll go ahead and read this the problem to give us some context, and then we will get started. Problem number 5 says this: I am loading supplies into my car. Assume that I push a cart loaded with 22 kilograms of equipment 300 meters out to my car at constant speed. The cart has a coefficient of kinetic friction of 0.3 as it rolls. Assuming I always push in the direction the cart goes, how much work have I done? If it takes me 8 minutes to push the cart out to my car, what is the power supply in watts? So for our scenario here, we're looking at problem number 5 on the review. We've got an object that we're pushing, a cart, and we want to figure out how much work we're doing as we push the cart. So assume here's our cart. Inside the cart, we've got a lot of supplies, stuff we're moving out to our car, and it's kind of a handle. So assume we're pushing on the cart, and we're getting the cart moving some distance, told it's 300 meters, so maybe we're pushing this across a long hallway in the school or across a really big parking lot, possibly. It'd have to be a pretty big parking lot for it to be 300 meters, but we're pushing the cart a long way. And we want to figure out how much work we are doing as we push the cart. Now, because I have a delta x, a displacement of our object, that means I might want to use our work equation where the delta x value shows up. As we've discussed, there are a few ways we can think about work as a quantity. One of them is by this equation. Work done is equal to the force applied on an object multiplied by the displacement of the object multiplied by cosine of the angle between the force and the displacement. Now here we're told the delta x is 300 meters in our problem. We can also probably assume that in order to get our cart moving in a certain direction, we're going to have to push on that cart in the same direction. So, if we're pushing out to the right, we're moving out to the right, the angle between those would be 0, because our force is in the same direction as our displacement. So really, if we think about what we need to find the work done with this equation, we already know delta x, and we already know the angle between our force and our displacement. So now it's a matter of figuring out what is that force. Well, in order to find the push force, we would probably have to look at some of the other forces on the cart. We're told that there's a force of friction, so we might need to account for that as well. So here we go. Let's draw a free body diagram to show our push force. And as we push, we're told that there's some kinetic friction, or it's really probably what we would call a rolling friction here, but we can approximate it to be similar to a force of kinetic friction as the cart is pushed out to the car. Now as well, probably safe to assume that we are on or near Earth's surface, so there's a force of gravity from the Earth on the cart, and the cart is in contact with the ground or the road, whatever we are pushing the cart across. So at this point, we need to figure out what is our push force. That's the force we apply to get the cart moving. So we maybe look at Newton's second law, specifically in the x direction. Sum of forces equals mass times acceleration. Now in the x direction, we have two forces. Our push force, I'm going to refer to that as a positive force because it's to the right, which is the traditional positive x direction. Minus f sub k, I'll subtract that because our force of friction is in the negative direction. So even though Newton's second law has us sum up our forces, here we'll have to subtract one of them because of the direction involved. So the sum of forces equals mass times acceleration. The problem statement tells us we're moving at a constant speed, which means therefore our acceleration will be 0. So now I know that my sum of forces equals 0, which can then set up this relationship that our push force is equal to our force of friction. which is great because we have a way of calculating for the force of friction. So now we have a way to find the force we need, which will go in our work equation. So from here, well, our force of friction, we have an equation to solve for that force. The force of friction is equal to the coefficient of friction multiplied by the normal force. Now, the problem tells us what our coefficient is, but we don't necessarily know the normal force yet. We can probably assume it's equal to the force of gravity here, but we want to be able to show why rather than just making that assumption. So let's write out Newton's second law for the y direction. Sum of forces in the y is equal to mass times acceleration in the y direction. Now in the y direction we have two forces, our normal force, which was directed upward, and our force of gravity, which was directed downward. Technically these are vectors, so I should be representing those. My apologies. And again, we're moving at a constant speed. We're also, could probably assume we're not moving at all vertically. So our acceleration in the y direction would be 0, and our mass times 0 would just equal 0, right? So now I can move my force of gravity over to show that my normal force should equal our force of gravity. So that's a relationship that will help us to find our force of friction, right? Our coefficient multiplied by the normal force. So here we go. Force of gravity on an object is equal to the mass of that object multiplied by acceleration due to gravity. Our mass here looks like 22 kilograms. So F sub g is equal to 22 kilograms multiplied by 9.81 meters per second squared. So I'll multiply those values together, 22 and 9.81. We get a value of about 215.8. That would be a force value, so we'll measure that in newtons. So now that we have that force, remember, that's not the force we need. We need the push force. This is the force of gravity, which we've said is equal to our normal force. So now we'll bring that value up here and find my force of friction. Our coefficient of friction here was 0.3. So 0.3 multiplied by 215.8 newtons. We end up getting a value of about 64.7 newtons. Now, this value will become very important because this value is our force of friction, which, as we showed earlier, is going to equal our push force because we're moving at a constant speed. Now, this is a really common misconception. Don't think that just because those forces are equal means our object cannot be moving. The fact that our forces are equal or balanced means our object is not accelerating, is what Newton's second law tells us. At some point in time, we would have had to push with a greater amount of force to get the cart moving, but now that it is moving, as long as our forces are balanced, we can continue moving at a constant speed. So now that I know my force pushing on the cart, I know my delta x, I know my angle, it's really a matter of using our equation one last time. So the work done here would be our force, which is 64.7 newtons, multiplied by our displacement, 300 meters, multiplied by cosine of 0 degrees, which will just be 1. So I'll take 64.7 multiplied by 300, multiplied by 1. And I get a value of the work done of approximately 19,420, round this up, 424 joules. That is how much work we do as we push on the cart. Now to finish, the last part of this asks us for a power value, right? It says here, what is the power we supply in watts? So power, remember, is simply a rate at which work is done, work over time. We know our work, we just need our time, but we need that to be in watts. A watt, as we've talked about in class, is measured in joules per second. So we first need to convert our time to seconds. So here we've got 8 minutes. 1 minute is equivalent to 60 seconds. So 8 multiplied by 60 should be, double check here, 480, just to make sure. So now we'll take our work done, the 19,424 joules that we just found, divided by our time, 480 seconds. So 19,424 over 480, we get about 40.5 watts. This would be the power we supply as we're doing this amount of work. Remember, power is just the rate at which work gets done. So, hopefully this gets us going in the right direction on problem number 5 on the review. As always, if you have questions, don't forget to direct those my way. There is one last thing I'd like to discuss here that doesn't necessarily go into mathematically solving anything. It's more of a conceptual question. Here, we're told that we're moving the cart across roughly level ground and we have a constant speed. So it sounds initially like, there isn't really much of a change in energy here. Even though we're applying a force, even though we're mathematically doing work, why doesn't that necessarily get us to a change in energy? So in order to illustrate this a little bit better, I'm going to draw an energy graph, a way that we've kind of visually been depicting energy. So the way that we set these up is by using a few different graphs to show initially what's happening in our system, the object that we are focusing on, and at the conclusion, a final graph. Now here, in the context of our problem, we can pretty much ignore spring potential energy. We're not told anything about a spring. And we can also probably ignore gravitational potential energy because our object is mostly moving across flat ground. We're not told anything about the heights changing. We are, however, told that we are moving at some speed, and we're told that that speed is constant. We're also not told anything about the mass changing, so if we think about kinetic energy, 1/2 mv squared, if our mass stays the same and our velocity stays the same, that probably means that our kinetic energy has to stay the same. Right? Now our system here would be our cart, right, with our supplies in it that we're pushing across the ground. And we just calculated that we apply a force, our push force on the cart, and we do a whole lot of work here. Was it 19,424 joules? How do we account for that? Because it looks like the energy we start with has to equal the energy we end with. But somehow we're doing some work, right? Come back to the free body diagram that we drew a moment ago. As we are pushing on the cart, remember, there's another force that's acting here. That would be our force of friction. Now, force of friction was the mathematically equivalent to our push force. Our force of friction is also active for the entire 300 meters. The angle involved might be a little bit different though. Our force of friction was to the left, we move to the right, which means our angle there might be 180 degrees. That would mean our work done would then be negative. So actually, as we are doing work, the force of friction is also doing work. And as long as our total energy does not change from start to finish, friction would have to do the same amount of work as our push force. Now, that's not really part of exactly what the question was asking, but it is an important thing for us to see. That here, the work that we are doing is just the work done by our force, not the work done by the other forces here. Right? Any force can do work on an object as long as it, usually causes some type of displacement and it's somewhat aligned with the direction of motion. Sometimes, depending on the angle, forces will not be able to do work. But it is important that we are able to take a moment and to talk through this idea conceptually and show what's really going on with all of the energy in our system. So hopefully this gets us moving in the right direction on problem number 5 on your review. As always, if you have any questions, don't hesitate to ask. Good luck.